All right, so I'm going to have you read a lot on your own for this section because I don't want the video time to run too long. But I will do another example here for the sake of demonstrating and narrating. And this one is an implication, and it's another one of these one-way implications. These are always fun to think about why one direction works and the other doesn't. So this is for all x phi or for all x psi. Implies that for all x, either phi or psi. So let's add some flavor and replace these by some English propositions. So for phi, let me try x is red. And for psi, let me try x is spiky. So I'm just doing something that I think I can draw. So let's imagine, what does it mean to say that for all x, that either for all x, x is red, or for all x, x is spiky. So let's write down the left-hand side and the right-hand side of this derived rule. So let me just write it in English without mentioning the quantified variable x. So for all x, x is red. That just says everything is red. And then for all x, x is spiky. That just says everything is spiky. So this or statement is saying either everything is red or everything is spiky. Let me just write that. All right, so what I've written here is the left-hand side there, the hypothesis of the implication. And the conclusion of the implication is, for all x, either x is red or x is spiky. So, in other words, everything is either red or spiky. And then the derived rule as a whole is saying, if either everything is red or everything is spiky, then everything is either red or spiky. So hopefully that does sound intuitive. If everything is red, then everything is either red or spiky, and if everything is spiky, then everything is either red or spiky. And hopefully you can also see that the converse, that if I reverse this arrow, that doesn't work. So to convince you of that, maybe I can draw an example world where it's true that everything is either red or spiky, but it's not true that everything is red or everything is spiky. So let me put in this red thing, which is not spiky, and this blue thing, which is spiky. And maybe a green thing, which is spiky. And how about also a red thing, which is spiky? Okay, so if this is our universe, and that's the universe only has 4 things in it, which is these things, then would you say it's true that either everything is red or everything is spiky? And would you say it's true that everything is either red or spiky? So think about those. Think about whether this is true about the universe here and whether this other thing is true. And okay, so hopefully you thought about it, and now here's what I would say is the answer. So it's definitely true that either everything is red or spiky. If you look at any particular thing, it's going to be either red or spiky. Like this one, it's red. This one, it's spiky. This one, it's spiky. This one is both. So definitely it's true that it's either red or spiky. So the conclusion of the implication, this, is true about the universe here. However, the hypothesis is false. So for this universe, I'm sorry, I have underlined the wrong thing up there. No, yeah, that's right. Yep, sorry. Yeah, so the hypothesis here is false. Everything is red or everything is spiky. That's not true. For this to be true, it would have to be either this would have to be true or this would have to be true, right? But they're both false. It's not true that everything is red. Just look at this blue guy. And it's certainly not true that everything is spiky. Just look at this smooth guy. So what I'm trying to convince you here is that this implication really goes one way. You cannot get an equivalence. And this is meant to convince you because here's an example where, for an equivalence, you would have to have both propositions hold or fail to hold together. The true or false becomes linked. And here's an example where one is false while the other is true. That doesn't prevent us from proving the implication, the one-way implication. It's just you can't prove the other way. Okay, so let's prove this one way that does work. So proof. And let's write it like this. So instead of writing it with the Greek letters, let me prove specifically this. So this is what I'm proving. The claim is this. If everything is red or everything is spiky, then everything is either red or spiky. So assume, assume that either everything is red or everything is spiky. So assume the hypothesis of the if-then. So for all x, x is red. Or for all x is spiky. Then my goal is to prove that everything is either red or spiky. So I'm just remembering now that my goal is to prove for all x is red, or x is spiky. I'm not going to include this goal in my proof. This is just maybe part of my scratch work. I'm just keeping it in mind that this is my goal. So I'm going to do universal generalization. That's how you prove a for all statement. Okay, so that means I should say consider any x, and then make sure I keep x arbitrary throughout my argument and try to prove that x is red or x is spiky. Okay, well, to get anywhere, so let me just do that. So consider any x. And now my goal is prove, without ruining x's arbitrariness, prove that x is red or x is spiky. Okay, well, what do I have to use? I have this or statement to use, right? So the only way really to make use of this is, other than using some derived rules, but I can't think of any useful ones right now, is to use the basic rule for using an or, which is proof by cases. So there are two possibilities. Either everything is red or everything is spiky. So case one, suppose that everything is red. And case two, suppose that everything is spiky. And the goal is, in each case, to reach the ultimate goal. The ultimate goal was this. X is red or X is spiky. So I hope that in each case I can reach X is red or X is spiky. So here I'm supposing that everything is red. Well then, in particular, X is red, right? Then X is red. If everything is red, then X is red. So, have I reached the goal? X is red or X is spiky? Yes. So X is red or X is spiky. This is that basic rule for OR, which says that to prove an OR, you can just prove either one of the two disjuncts. So prove phi and you get phi or psi. Prove psi and you would also get phi or psi. So that's it for case 1. We reached the goal, which was X is red or X is spiky. And then for case 2, suppose that for all X, X is spiky. It's pretty similar. Let me just fill that in. So then in particular, X is spiky. We're supposed that everything is spiky, so in particular X is spiky. And so X is red or X is spiky. And so that's it for the proof by cases. So since so let me write a little bit less. So let me just say therefore. So this therefore is outside the proof by cases. And saying therefore X is red or X is spiky, since we drew that conclusion in every case. That's how proof by cases works. Whatever conclusion you can draw in every case, you can draw outside of the proof by cases. And look, we said consider any X, and we proved that X is red or X is spiky. And X remained arbitrary throughout, so we never had to make any assumptions about X to do this. So then, for all X, X is red or X is spiky. Okay, so that's it, and I guess I'd like to just go over it and show you and just annotate with where different things were used. So hopefully this is what you will do when you read these derived rule proofs on your own, is go through and figure out where the different quantifier rules are being used. So here, this consider any X, that's the beginning of a universal generalization. So a UG is starting here. And the goal of that consider any X is eventually we want to prove this about X. That's where the UG ends. So here, or if you like here. So it ends here, but then this is the conclusion that you get from doing the UG. Alright, so that's one quantifier rule. And another one that shows up is universal instantiation. So these lines where you say everything is red, so X is red, for example, here. This is universal instantiation. Everything is spiky, so in particular X is spiky. That's universal instantiation. So this gives you kind of... okay, I also want to give you a way of thinking about the four basic quantifier rules. So this, the blue brackets here, the UG, helped us go from, in the end, what it enabled is going from X is red or X is spiky to for all X, X is red or X is spiky. So what it did is it created this quantifier. It took a proposition that didn't have a quantifier on it and it tacked it on. That's generalization. Tacking on a universal quantifier, saying, oh, I know this about arbitrary X, so then I know it about all X. So UG has the effect of adding on a universal quantifier. Similarly, UI, look at the effect of UI. It has this effect of deleting a universal quantifier, right? It took this, everything is red, and then it went to X is red. So it deleted this. So this is one way to view the UG and UI is UG creates a universal quantifier and UI removes one. And similarly, e.g., existential generalization, finding an example to prove that something exists that satisfies a property, e.g. creates an existential quantifier. And EI, existential instantiation, removes an existential quantifier for the sake of an argument. So that's a kind of oversimplified way of thinking about what they do. So here's the oversimplification that I just made in diagram form. UG creates a universal quantifier, UI will remove one. EG creates an existential, and EI will remove one. And I guess the kinds of caveats that I would add are things like, okay, when you use UG to generalize from, X is red to everything is red, it had better be that in your argument X was arbitrary. And you saw how subtle that can be. So there's some fine print there. And EI is the other one that has very fine print. It says, X, when you instantiate, when you go from something is red to X is red, X had better be a brand new variable. Where there's no previous assumptions about X. It's kind of also like similar to saying it's arbitrary. And this is also a massive oversimplification because it's not, it looks like it's telling you, it looks like an implication arrow. These are not implication arrows. So it's not quite that you can deduce phi from there exists X such that phi. That wouldn't make any sense. It's more like you can introduce phi as an assumption into your argument for the sake of the rest of the argument. So this is not an implication arrow. This one is, let me just put this, exclamations, warning, this is not an implication arrow. It's more like something like proof by cases, where it's saying, it's providing a strategy for proving another thing, like omega. Whereas, on the other hand, these two actually are implication arrows. These, you could view them as implication arrows. Similarly here, it's not quite an implication arrow, it's an argument strategy. And maybe some other annotations here. When you do a UI, when you apply phi to a particular case, you can apply it to anything, so it's not necessarily X. So you can apply it to whatever you want. Phi with X replaced by anything you want. And when you do EG, it doesn't have to be that you proved phi about X. So if you want to prove that something is red, you can do it by proving X is red or Y is red or 17 is red. Just prove that something is red to prove that there exists X such that X is red. So it's sufficient here to prove phi with X replaced by any old term, and that would be enough. Okay, so that's a super crude kind of summary.